So another problem that we have is that if I try to explain to predict the age of the captain as a function of the size of his boat, that might not work extremely well. So I might need to add extra information. And I could add, for instance, the age of his daughter, and that might help. So then I'm trying to predict the age of the captain as a function of the size of the boat and the age of the daughter, and I'm going to find a combination of the two. Okay, so intuitively what we're doing is instead of fitting the data in 2D, we're fitting the data in 3D when we have 2 parameters. And if we add more parameters, because this is slightly limited, right? I could add even more parameters, the number of kids he has or things like this, then we're just building a space that is bigger and bigger and bigger, okay? That's the intuition. It's a very powerful intuition to have. I understand that it may be hard to have intuitions in spaces of 50 dimension, but believe me, you can train yourself. So the problem that we get is that as the space becomes larger, it becomes empty, because we have only a small number of data points compared to the dimensionality. So here, I've shown you that with 2 data points, basically, I can't decide which plane goes through, which is the best plane that goes through, even if I have only 2 features, only the length of the boat and the age of the daughter, okay? And it gets worse. So what I'm telling you is that if I'm adding features that should help me describe, that should help me predict, I have a harder statistical problem. So people think they have more data, but it's harder. And it grows harder exponentially. And this is what's known as the curse of dimensionality. The reason it's exponential is you would have to pave this space regularly if you wanted perfect description of the data. And for this problem, we also need a regularization. It's the exact problem as noise. Dimensionality is like noise. It is preventing us from seeing the signal. So the more parameters we have in our model, the more we need to have either more data or more regularization, okay? And so to give you an example of regularization, suppose I'm trying to learn to predict data that's on this sine wave, okay? I can use a model, which is an approximation model, which is that I'm going to approximate the data as constant, as piecewise constant, okay? So basically, because the data is piecewise constants, this is what's going to be x, and this is y. And I'm saying that if x is between 3 and 3.5, then y equals 2. And then if x is between 3.5 and 3.9, then y equals 2.3. Okay, you get the idea? So by the way, this is known as a tree. And the reason that it is a tree is that it's a decision tree, because you're saying if this, then go in this direction. If this, go in this direction. Okay, so you're going down a decision tree. So just to tell you, all the tree methods are like this. Okay, so what you can see here is it doesn't fit the data very well, because I'm trying to approximate a continuously varying function with constant values. So then what people do is that they use an ensemble of trees. So the idea being that they fit more and more trees, and then they combine them in a certain way. So here, this is a combination of 300 trees or 300 staircases that have been fitted in a certain way. And the trick, and I won't describe the details, but the trick is to fit the trees in a way that averages the noise in a certain way, okay? And this is typically a random forest, even though what I'm showing you here is not a random forest, but a gradient boosted regression tree. But they're the same family of model, okay? So what I wanted to say here is that your model doesn't have to be correct. We're using a model of piecewise constant, which is quite clearly incorrect here, but it's a convenient model. And the reason why it's convenient is that these trees can be run in an extremely fast way. They're just a collection of if-then statements. So if you code them in low level, they're extremely, extremely fast, okay? So one of the different reasons why these models works extremely well is that we can run them many, many times and then average them, and this gives them a lot of robustness, okay? So if I can do a bit of a summary on the elements of a machine learning method, and I have a tiny bit of math, I hope you won't hate me for this. We're using a forward model, which is that we have a function that describes what we're trying to predict, like the age of the captain, as a function of the data observed. The data may be the size of his boat and the age of his daughter, and parameters that we're trying to adjust. This function could be a linear model, but it could be anything else. All I need it to be is a function in the computing sense, which is a function that I can execute, gets data in, returns a value out. I don't need specific details. Well, in general, I don't need specific details on this function. Okay? So it's a set of rules that go from x to y. I need some form of measure of error to be able, well, usually we use this measure of error to train the model, and we also use this measure of error to test the model. So typically, if you're using random forests or gradient boosted regression trees, you can tune them to minimize the mean squared error or the minimum absolute error. And those are two different measures, and we could discuss what properties they have, but I think this is for further discussion, okay? And then what we need is the notion of regularization. And it can be given by choices in the model. And my tree-based models, they have constant values, okay? That is a regularization. Because they have constant value and because they have a small number of staircases, they don't fit the noise, or they don't fit too much the noise. That's the important thing. Or they can be given by a penalty. A penalty would be basically an explicit bias on the parameters of my model. And an example of a very common and useful penalty is to say that if I'm looking at data in the wild and I'm just trying to do correlations between things I observe, I shouldn't trust my correlations because I will get high correlations in random time series. So what I need to do to get a good model is to do these correlations and then decrease a bit the observed value of the correlation to trust it. And by how much I decrease is a difficult choice, but this is a form of penalty. I'm just giving hand waving, not math here. Okay? So that's all nice and good. But many people, when they hear this, they're like, yeah, sure. How does this relate to my data? I don't have numbers, I have text, I have databases, and as always, you mathematician, you like to do nice drawings in 2D and curves, but this is not my problem.